Hello, everybody. Welcome to this NASA Goddard Google Plus Hangout. We are here to watch the battle between Fire and ISON. That is Comet ISON, which today is making its slingshot around the sun. I am Karen Fox here at NASA Goddard Space Flight Center in Greenbelt, Maryland, and I'm in the Solar Dynamic Observatory Mission Control Room. We will be taking your questions live during this Hangout, but first we want to show you right away what SDO is seeing. So I'm going to hand you right over to solar physicist Alex Young.
Hello, everyone. It's great to be here. And we're going to show you now the images that we have from SDO, which have come in from its first off-pointing. So can we switch to... Okay. All right. So currently what you're looking at is the first of 3 off-pointings that SDO is making. This particular one is showing the approach of the comet, or will hopefully show the approach of the comet soon. Now at this point, as you can see or not see, there isn't an obvious image of the comet ISON. What we should be seeing is it should be coming in from the bottom right of the image heading towards the upper left. Now, the problem with looking at these kinds of images with the extreme ultraviolet is we're normally looking at the sun, and now we're looking very far off the sun. So it's very difficult to see these. We have to change the contrast, and at the moment we don't see anything, but what we're hoping is that soon as it gets closer to the sun, it becomes brighter, we're going to start to see a signal and start to see some activity. But at the moment, we are in fact seeing it very well from the SOHO spacecraft. Now, SOHO is seeing it coming in the coronagraph C3. That's what you're seeing on it's the blue image. Now, that white circle that you're seeing is the sun, and in the bottom right, you see that bright object streaking in, and that is Comet Lovejoy. And as it's coming in, sorry, Comet ISON, as it's coming in, you can start to see the 2 tails, the dust tail and the ion tail. The dust tail is following the trajectory of the comet, but the ion tail or plasma tail is being influenced by the sun's solar wind. And as these directions change, you'll start to see the path of that change. And as it gets closer and closer in, it's going to start to get brighter and brighter, and you're going to start to see pixel bleeding, just like you do for some of these bright stars. And then we have also seen this with the inner coronagraph, the C2 coronagraph. And let's see, we don't have that? Okay. We'll show you that in a second. Oh, actually, right now what we have is an image. So this on the left is an image that was created by the STEREO SOHO team to show you the path that ISON is expected to take based on all the calculations. And on the right is one of the first images of the actual data. And what we can see here, the reason we're showing you this is it's basically on track. It's following the path that we expect. Now, there's been a lot of chatter on the internet for the past couple days about whether or not ISON is breaking up, and I even saw something recently that it's exploded. Well, we certainly don't know exactly what's going on inside the nucleus, which is much smaller, but we can definitely say it's here, and it's for the most part intact. It continues to get brighter as we expect. So I think that we're on track for a really, really spectacular show. Now, once we get through the images from the first off-pointing, we've actually already started to prepare for the next off-pointing. So we're going to move the spacecraft up to the left, and that's going to show us the area of closest approach, what we call the perihelion. Then we have one more off-pointing after that, which will move higher up and to the right again to show what we call the departure of the comet. So we turn it over to Karen now.
Hello again. We are, as I said, going to be taking your questions live. So you should send them. You can do it by the YouTube comments. You can send it via Google Plus Hangout or on Twitter. Go ahead and use the hashtag ISON, I-S-O-N, or hashtag AskNASA. And let's start out with some real basic questions, Alex. Can you tell us what ISON even stands for?
Well, so ISON stands for the International Scientific Optical Network. Now, the way comets are generally named, it's a little bit complicated, but when they're discovered by amateurs, they're named after the amateur or amateurs. When they're discovered by a spacecraft, such as SOHO, they're named after the spacecraft, and they're given a designation for the number of the comet. In this case, this was discovered by professional astronomers from Eastern Europe, two astronomers, and they discovered it using this particular network, hence the name ISON. And so the official name for this particular comet is C/2012 S1 ISON. And this is the general kinds of convention that we're going to see for comets that are discovered mostly with ground-based telescopes. Now, one thing that I'll mention here is this particular kind of comet, we call this a Sungrazing comet, is not unique in the sense that we've seen a lot of sun-grazing comets. Now, up until the launch of the SOHO spacecraft, we'd only seen a handful from space and a handful from ground. But now, the SOHO spacecraft and the LASCO coronagraph on the SOHO spacecraft is seen somewhere on the order of 3,000. So we see almost a comet a day. But most of the comets that we see from SOHO are much smaller than Comet ISON, and so they basically evaporate when they get close to the sun. This one we're very excited about because it's much, much bigger, and based on the two previous comets that we've seen in SDO, we are very certain that it's going to make it around and give us a spectacular show. Now, I'll mention that the last comet that we saw from SDO, Comet Lovejoy, was observed both going towards the sun, behind, and then it was seen after it came from around behind the sun. This particular comet ISON is about 10 times bigger than Comet Lovejoy, and this is one of the reasons that we have a really good indication that it's going to make it. Now, Comet Lovejoy, when we watched it, we were all really, really excited. We all watched the data coming in just like we're watching it now. And many of us really didn't know if it was going to make it out. So we saw it go behind the sun, and we waited and waited, and sure enough, we got a really amazing surprise. Now you can see here, we're looking at it in the 171 angstrom wavelength from SDO. This is extreme ultraviolet. And there's a little tiny wiggle you see in almost the middle of the video. That is Comet Lovejoy as it's making its way from behind the sun. And we were able to do an amazing amount of science, not only just on comets, but we're able to study the solar atmosphere itself because the comet's material left a tracer as it traveled and wiggled its way through the atmosphere and traced out the magnetic field. There are huge, powerful magnetic fields coming out of the sun's surface up into its corona, but they're not really visible. They're only visible when we're looking at really bright structures that are traced out. And in this case, we can see the magnetic field much higher up in the atmosphere in a way that we normally couldn't see. This is extremely difficult to measure.
Great. Thanks a lot. I'm going to throw you one of our first questions in just a moment. Before we get there, I want you to know that we are going to have with us shortly Dean Pesnell, who is the project scientist for NASA's Solar Dynamics Observatory. He is in the process right now in the mission control room with us, and he is working with figuring out where the camera is going, and they're getting set for their next pointing, next change in where they point. And so he's working with them, but we're hoping to talk to him shortly as well. We have some some other scientists joining us along the way. Carl Battams from the Naval Research Laboratory will be joining us from Kitt Peak Observatory, where they are watching the Sun and Comet ISON with a ground-based telescope there. And we will also have Phil Plait, who is a blogger. I think he's known as the Bad Astronomer on Slate.com. So they'll be coming along soon. We have started to get in some of your first questions. So let me share a first one, and Alex, you may answer this for us. And I think it's the question a lot of people who've been tracking the comet are wondering. The question from Sebastian Basaldua is the comet still in one piece? What do we know?
Well, that's a really good question, and we've been keeping in touch with a lot of the professional astronomers, in particular our colleague that we'll hear from later, Carl Battams, who's been keeping us informed of what's going on. And for the most part, as far as we can tell right now, Comet ISON is still intact. Now, the problem, as Carl pointed out, is we really aren't going to know for certain until after the fact. But every indication is right now it's following the expected path, the expected brightness, and so it seems to be very much intact, and this is why we have still a lot of excitement and a lot of hope for what's going to happen.
Great. It's exciting to be here now trying to see what's going to happen on Comet ISON. For anybody who is just joining us, we are here at NASA Goddard Space Flight Center in Greenbelt, Maryland, in the Solar Dynamic Observatory Mission Control Room. And while NASA has been watching Comet ISON with a lot of observatories, today is the final slingshot around the Sun, and SDO is the tool we are using to try to see it. We are taking your questions. Go ahead and use the hashtag ISON or Ask NASA. And I'm going to send out another one, which is another question we've been getting a lot of, which is from Zeno Jansen. And he wants to know if any part of the comet could hit Earth.
Well, the immediate answer is no. We're not expecting the comet is not going to come very close to Earth when it makes its closest approach. Now, there's always the possibility that maybe we would pass through a little bit of debris, give us a little bit of shooting stars, but the comet is not coming anywhere near the Earth in terms of being a danger to us. So there's no concern about it hitting the Earth. And actually, one of the things we'll do is we'll let our expert Phil Plait talk a little bit more about this. I know he's written a book about cosmic catastrophes.
Great. Well, let me throw it on over to Phil. I introduced him just moments before he joined us, but I will remind you, Phil Plait is joining us. He is the Bad Astronomer on Slate.com, and he will be joining in on this this great live Google Plus Hangout as we watch to see if we can see Comet ISON going around the Sun, as well as what shape it is in. So the question that was asked, Phil, and I'd love for you to chime in, is whether or not Comet ISON could possibly affect Earth. And I suspect you've been getting similar questions on your blog.
Hi, yeah. Actually, let me make sure. Can you hear me right now?
Yes, we can.
Okay, excellent. Can Comet ISON affect us here on Earth? The answer is no, not physically at least. It's not going to come anywhere near us. It came in at an angle to the Earth's orbit around the Sun. It's going to swing around and head back out at an angle to the Earth's orbit. And it hasn't even come anywhere near us so far. The closest it's going to come is actually not going to be for about a month on December 26th, when it's going to be 60 million kilometers, or about 40 million miles from the Earth. Now, 40 million miles is a long way. To give you an idea, the Moon is only 250,000 miles away. So the comet won't get any closer to us than 150 times the distance from the Earth to the Moon. So really, nothing's going to happen. And even if it swings around the Sun and breaks up, and it's as I look at the clock right now, we're getting pretty close to perihelion. This is very exciting. Even if it breaks up and spreads out a little bit, it's not going to spread out so much that any big chunks are going to hit us. So we're perfectly safe.
Well, since we're 2.5 hours in this Google Plus Hangout, and we haven't actually yet answered one of the most fundamental questions that I think people may be wondering, which is what is a comet, and what is interesting about ISON per se? So I'll throw that to both of you. Why don't you talk about that a little bit, please?
Go ahead, Alex. You're the expert.
Okay. Well, so a comet is, simply put, it's a big chunk of ice and rock that has been around for about 4.5 billion years. It's a pristine piece of the material when the solar system was formed, the sun and the planets. And so that's one of the things, or one of the main things that's so exciting about a comet, is it's like a fossil. It gives us an opportunity to look at what the material was like, what the conditions were like 4.5 billion years ago. Now this particular comet is also pristine in that it's never been past here before. It hasn't been by the sun, and so it hasn't felt a lot of the harsh environment that's caused a lot of its material to waste away. This one's taken about, I think, 50 million years or so to get here from a place called the Oort cloud. And looking at the orbital dynamics, it's got what we call a hyperbolic orbit, so it's not really going to come back. So this is a once-in-a-lifetime thing. It's coming in past the sun, and it's going to head right back out, and we're never going to see it again. That is, if it makes it. Now, from a solar physicist point of view, which is really my area of expertise, this is exciting because not only do we get a chance to learn about the solar system, but the comet is giving us an opportunity to probe the outer atmosphere of the sun, the corona. Especially, it gives us a chance to study the magnetic field of the sun. Now, we can study the magnetic field of the sun very close to what we call the solar surface, but as we get farther and farther away, it's much more difficult to study. And out in the outer corona, it's almost impossible with the kind of technology that we have. So that's really what's really exciting about it. So we're going to turn it back over to Phil and let him give us his take on it.
Phil, I can't hear you. Phil, can you turn your microphone back on?
There we go. Sorry about that.
There we go. Thanks.
There's so much going on right now. I'm typing and trying to get the latest pictures. Actually, a new picture from SOHO taken as recently as 1724, so 5:24 p.m. Universal Time, which is 12:24 Eastern Time. I try to get this all straight. Shows the comet, actually, the nucleus is not as obvious as it was a little while ago. I don't want to speculate too much, but that could indicate that something has happened, that it's fallen apart. It could simply be that I'm looking at the image right now, and I'll have it up on very soon. I'm sure we'll have it here very soon, too. It's hard to say. There's been some chatter that the nucleus of the comet, the solid part of it, had broken up, but there's been nothing definitive yet. Hopefully the SDO images that we'll be getting soon will actually show something a little bit more detailed, and we'll be able to figure out what's going on.
And speaking of SDO, we have just had another scientist join us. We have Dean Pesnell, who is the project scientist for the Solar Dynamics Observatory, joining us here in the mission control room for SDO at NASA's Goddard Space Flight Center in Greenbelt, Maryland. So you will now be seeing both Alex and Dean in the same camera, and Dean can tell us a little more about what SDO is seeing and what we hope to see.
All right.
We are unfortunately not getting a good sound
That's my
from you
fault.
guys.
Okay, sorry.
That's because Alex.
That's because I forgot to. I muted him. I'm
He
sorry.
muted my microphone.
Okay.
That was not my logistical problem.
No, it was mine. Go ahead.
Okay, so we're going to try and follow the comet as it goes by the sun with three different pointings. We just finished the first one where we pointed down and to the left. Now we're pointed essentially to the left of the sun, and then about an hour from now we're going to point up and to the left. And that allows us to kind of follow the track of the comet as it goes by the sun. Other than that, we're just kind of just taking pictures.
Okay. Well, where are we in this in these three off pointings?
So we just finished the first off pointing, and we started the second. So we should be seeing the perihelion passage of Comet ISON. That's the time when it's closest to the sun and gives us the best chance of actually seeing the comet debris as it comes off. That should be at about 1:45 to 1:48 this afternoon. So in about a half hour or so.
Okay. Well, how long does it take between when you take those images to get them down here?
So we work really hard to get the images down from the satellite, and it takes about 10 to 15 minutes to get them to where people can see them.
Okay.
And I'm going to interrupt for just a second while we try and get Dean and Alex's microphone working a little bit better. There's a little bit of a feedback there. So they're working on that. So in the meantime, I'm going to pass a question to Phil while our team works on that. And here is a question that we got from Jeff Bohr. And it's an interesting question. It's a question about the dynamics of how things move through space. And the question is, how is it that here's the sun has been pulling on this comet for 5 million years. How come the sun misses? The comet misses. Why doesn't the comet fall into the sun?
That's a really good question.
So we're going to pass that on to Dean. So why doesn't the comet fall into the sun?
Well, it's really doing its level best to fall into the sun. But even though it's been doing that for several million years, at the last minute...
Sorry.
Oh, I'm sorry.
They asked Phil. I'm sorry. We had a little microphone confusion here, and I just cut him off.
Go ahead.
Oh,
So,
poor Phil.
Nope, I've lost him again. All right, then I'll answer the question. Can you hear me, Karen? Are we good?
Absolutely, I can hear you.
Okay.
I can't hear him.
The comet is orbiting the sun in the same sort of way that the planets do. And the Earth is going around the sun. The Earth is being pulled toward the sun, but it's also moving sideways at the same time.
Oh,
so it's always falling sort of into the sun, but always missing. That's kind of the way orbits work. And there are different kinds of orbits. The Earth is on more or less a circular orbit, just like the Moon is on more or less a circular orbit around the Earth. In fact, they're actually not quite. They're elliptical. They're stretched out a little bit. And the more you stretch out an orbit, that's called the eccentricity. It's just a way of physically describing the orbit. A circle has an eccentricity of 0. An ellipse has an eccentricity between 0 and 1. If you stretch that orbit out enough, it becomes a parabola, if you remember that from your algebra class. And if you stretch it out even more, it becomes a hyperbola. And all of these shapes correspond to sort of how the object is orbiting the sun. If it's on a closed orbit, if it continues to orbit the sun all the time, it's on a circle or an ellipse. If it actually can escape the sun's gravity, it's on a parabola or a hyperbola, just depending on how much energy the object has. Well, Comet ISON is coming from very, very far away. It's falling in towards the sun. It's going to skim right over the sun's surface and head back out, and it's going to miss, just like the Earth is always missing the sun, if you want to think of it that way. It's just that the comet gets much, much, much closer. Now, right now, we don't know exactly what the eccentricity is of Comet ISON's orbit. We don't know exactly the shape. It might be a parabola, in which case it just kind of goes off into space and always slows down, or it might be a hyperbola, which means it's going to go around the sun once and be ejected from the solar system forever. Right now, the measurements of this are extremely close to being a closed orbit versus being an open one. It's going to stay orbiting the sun versus getting ejected out into interstellar space. Hopefully, we'll know more in the next few days as we get better observations, more observations after it passes the sun. We'll be able to nail down the orbit even better.
Great, thank you, Phil. And now that we have the microphone issues worked out here in the control room at the Solar Dynamics Observatory for this live Google Plus Hangout. We're about to toss it back to Dean Pesnell, the project scientist for SDO. Before we do that, let me just remind you that we are taking your questions live right now. You may comment on our YouTube, the Google Plus Hangout, or send a tweet using the hashtag ISON or the hashtag AskNASA. So before the microphone troubles, Dean was telling us what we're hoping to see in the SDO imagery. So I'll pass it back to him.
So when we looked at Comet Lovejoy, we saw, oh, now I have to hold my own mic?
Yeah, just hold.
Oh, man. So when we saw Comet Lovejoy in SDO, we saw just a trail, and the trail actually lasts for quite a while. And so what we're hoping to see here is another trail of material behind the comet that lasts, for a while. We're thinking it could last an hour at the distance that this material is from the sun.
Do we know why it lasts so long? I mean, why can you see it for so long?
There's a chemical reaction taking place where the electrons from oxygen atoms are being stripped off. And that chemical reaction takes a little while, and hopefully that they'll last longer before the next time an electron gets stripped off.
Okay. So what are we seeing? What's the advantage of seeing that material as it travels on?
Because this material is stuck to a magnetic field, we get to see it moving along a magnetic field. So it's a real surprise for this cometary material. First off, millions of years ago, it was out in the middle of, half a light year away, and now all of a sudden, it's next to a star, it's really hot, they're losing electrons, and then they run into a magnetic field. And that magnetic field basically takes them, and from moving along the comet orbit, all of a sudden, that gas has to move along the magnetic field. And so we see this stuff take a right turn or a left turn and move away from the comet orbit. And it makes these little fan shapes that stay for a long time along the orbit of the comet. We actually can't see the comet in SDO. It's too small for us, and it doesn't glow for us. But the material it leaves behind glows very nicely as it moves along that magnetic field.
Well, I have a question. So we know that the corona is really, really hot. Okay, the sun's corona, millions of degrees. But what's the temperature that the comet really feels? I mean, how hot does the comet itself get?
So the comet is basically sweating like crazy because it can't raise its temperature above about 300 Kelvin, which is kind of a room temperature kind of thing, until it gets rid of all its water. As long as it has a lot of water around, evaporating that water keeps the temperature relatively cool. So that the comet actually is not very hot. There's probably spots of the comet that are very hot, where there's no water anymore, or where it's covered by some kind of rock, or there's a big boulder there, and that material can get very hot, several thousand degrees. But any place where there's water, it stays a reasonably comfortable temperature. As soon as it runs out, as soon as it gets out away from the comet, though, it's a different story. Then it starts running into that very hot material from the corona, and that heats it up and very quickly after that.
So if I was sitting on that comet and I was in the right place, it wouldn't be so bad.
Well, so I was one of the things I thought about when we were doing this was a sunrise on a sun-grazing comet. So if I was sitting all the way behind in the backside of a sun-grazing comet as it came in towards the sun, and I'd have this great view of the Milky Way, and it would barely know that the sun was there, as long as I stayed on the back, far from it. But as you get closer and closer, you would start seeing this rim of sunlight show up around the edge of the comet, and it would, kind of like a total eclipse, not quite total eclipse. And as you get closer to the sun, you would just see more and more of the sun showing up. And eventually, all parts of the comet will be warmed by the sun. So you'll be pretty hot, because remember, you're kind of stony stuff, so you would warm up pretty fast. You'd want to be buried down inside the surface of the comet.
Okay, cool.
Great. Our next scientist has joined us. Please welcome Carl Badams, who is at the Naval Research Lab and has also been involved with NASA's Comet ISON observing campaign. And he is joining us from the Kitt Peak Observatory, where they are watching this comet from the ground. And Carl has been very involved with watching ISON from the beginning. So I would love for him to jump in and maybe even give us a little history about what we've seen with ISON along its path and whether it's broken up already.
Hi, can you hear me?
I can.
Okay, fabulous. Well, it's a it's a long history. I guess it started back September of last year when ISON was first announced, and we heard it was going to be a Sungrazing comet, and so that immediately gets me nice and excited because I've been dealing with Sungrazing comets for 10 years now. And one of the really unusual things about Comet ISON is that we knew about it so far in advance. So normally we see a lot of Sungrazing comets, but they will usually appear in the spacecraft images maybe a few hours, or if we're lucky, a couple of days before they're completely vaporized. So we don't ever get to spend a great deal of time observing them, and we don't get to look at them in great detail because they just suddenly appear and then they're gone again. So Comet ISON really has given us an opportunity to I don't want to say leisurely, but to take our time and really get our ducks in a row and get a lot of assets together for observing the comet. And so I've been involved in the Comet ISON observing campaign, which is essentially a group of volunteer professional scientists who we've been working together to coordinate global observations of the comet. So that's ground-based, whether it's amateur astronomers or professional amateur astronomers or the big professional observatories, and in addition to that, spacecraft as well. So we've had, I think, 10 different spacecraft now observe Comet ISON, and we're hoping for a few more. Hopefully anytime now hopefully anytime now SDO will become, I guess that'll be the 11th one. And this has all been going on for, like I say, with the campaign, we kicked it off around March or so. So it's been a very long and busy year. We've had a lot of organizing to do, a lot of coordinating to do. We've been pulling in observations from different groups. We've been trying to analyze, get an idea for what the comet is doing, and then when we thought we knew what the comet was doing, we'd then pass that information out to the community so that they could better adjust their observations. Now, of course, Comet ISON has been weird, to say the least. That's the best description I have for it. I've been asked this question a few times, and I've said in a few interviews, ISON is just weird. It has behaved unpredictably at times. And when it's done something strange, we've spent some time sort of scratching our heads, figuring out, okay, what's it doing? And then when we think we know what it's doing, and we think we can predict what it's then going to do, it goes and does something different. So it's been outbursting. It's been sort of trending flat in terms of its brightness, and then it will start to fade, and then when we think it's dying, it will flare up again. So it's been a ridiculously dynamic comet. It's been fabulous to study. Unfortunately, this morning, I don't think the news for it is all that wonderful, but I'm sure we'll get to that.
Let's actually talk about that for just a moment, Carl and Phil too. You know, one of the things that's interesting about this comet is it's sort of good news for scientists if it breaks up, because we get to peer right into its heart, but perhaps not as good for people down on the ground. I'd love to hear about when we might see it down on the ground, what could happen if it breaks up, and also I know Phil has some pictures he wants to show us from SOHO right now.
Right. The comet's been visible in the early morning over the past few weeks, and it's been getting brighter as it gets close to the sun. Last night, it got very bright for a short period of time, and then appeared to start dimming in the SOHO images. I know Carl was tweeting out some pictures of that. That's pretty interesting. We weren't sure what to make of that. Well, I just grabbed the latest SOHO images, or the latest that I can find, that were taken at 1724 UTC. So you subtract 5 hours, that's 12:24 Eastern Time. And I put that up here on my screen, and you can see the black part is the sun itself blocked out by a little metal disc that prevents the very bright sun from overloading the picture. The red part is the narrow angle view using SOHO, called the LASCO C2 camera, and the blue part is the wide field view, the LASCO C3 camera. They almost, not quite align here. That's pretty close. And you can see that, you can see the tail sweeping away from the sun, the two tails, the dust and the ion tail. Interestingly, we're not really seeing the head of the comet. Usually there's a bright spot right at the tip there, and that's the actual head, the solid nucleus, which is way too small to see. It's probably 2 kilometers, about a mile across, but it's blowing out gas and dust, and that reflects the sunlight. That can be thousands and thousands of miles across. But from this distance, it still looks like a dot to SOHO. That's been obvious in the past few hours, past few days. Now it seems to be gone. We see this long, stretched out smear, and then it fades away and then gets bright again out in the tail. I don't want to overly speculate here. I don't want to read too much into this, but that to me looks like the nucleus may have broken up, and is now all these pieces are orbiting the sun. So we need to keep our eyes on that, wait for the SDO images to come in, but that's what I'm guessing right now.
And let's follow up on that, because we've got a Twitter question from Chris Holtz, who wants to know, if it's broken up, what information are we going to be able to get from that? What's the science we're going to be able to learn?
Okay, do you want me to take that one?
I figure you can all chime in if you want to.
Okay,
Go back and forth. Tell me what you all think.
Okay, all right, I'll take this one. If ISON does or has completely fallen apart, it's not particularly good news for ground observing, but again, that's something we'll get to in this chat in a minute. But in terms of what we might learn, comets, I think, as Alex has mentioned, they're the building blocks of the solar system. So all of the planets and everything we have in the solar system, they're all made of the same stuff that comets are, or comets were there before we had the planets. I think it was Casey, who is on the campaign with me a couple of days ago, he had a really fabulous quote that when you're building a solar system, before you can build planets, you have to build comets. And so we want to learn what the comets are made of, and when we see one completely fall apart, then that really gives us a very unique opportunity to look at what it's made of, what it's composed of. And in addition to that, and this is what's kind of handy, I guess, about sun-grazing comets, is particularly like Lovejoy or ISON, if they do fall apart in the solar corona, they're in a ridiculously hot environment, and literally every single piece of material that the comet is made of is going to vaporize. In a typical comet that's kind of far out from the sun, the ices are always boiling and vaporizing. That's a standard behavior for comets, but you have to get very, very close to the sun for the rocky stuff to vaporize. And in fact, it was only probably, I think it was around maybe 18 hours ago that ISON got close enough to the sun that the rocky material would also start to vaporize. And indeed, that may be partly why it's not doing so well right now. But so when we see all of this material, the entire thing completely vaporizes, we can kind of look at the light that comes from that. We can analyze these images, and that gives us a really, really unique view of the composition of the comet. And it's a view that we would never have any other way of obtaining that information.
Well, I want to remind everybody that we are having this live Google Plus NASA Hangout from the Solar Dynamics Observatory Mission Control Center in NASA Goddard in Greenbelt, Maryland. And the point of this is we're supposed to be looking to see if we can see ISON during its perihelion, its closest approach to the sun, in the SDO cameras. And I have a question from a journalist, from Alan Boyle from NBC News. And I'll throw this to Alex for starters, and if the rest of you want to join in, please feel free. But he wants to know what do we make of the fact that we can't see ISON and SDO right now? Maybe we can look at some of the images from SDO, some of the live images right now. And Alex, let me know, should we be worried that we can't see it?
Well, my first response would be no, we shouldn't be worried. I mean, one of the things we have to understand is that looking at these images is very difficult, and oftentimes we have to do some processing. You know, we have SDO is not made to look this far off the sun, and there's a lot less signal than we would normally get, and so consequently we have to do some contrast changes, and we also have to do what's called backgrounding the images. We have to take away stuff that was there before and subtract it out or somehow adjust it. So one of the things that we don't know yet is it really there? Is the signal there, and we just haven't got the images processed correctly? So that's one thing. The other thing is that it's much farther away from the sun than Comet Lovejoy was, and so there's a lot less material in the sun. The magnetic field is a lot different, so the conditions are different. So in some ways, not seeing it is also telling us something about the specifics of the conditions. This is an area of the sun that's very, very difficult to study, and so having this comet there and having this tracer is putting it into an environment that we're not used to before, and so I think that this is a unique situation. So it may still be there, but also the fact that we're not seeing it is telling us something about the environment. So that's sort of my basic take on it. Perhaps Carl might have some more thoughts about that.
Hi, Alex. Well, it's hard to say. I mean, it's hard to know what the comet is doing right now. We don't know what's left. We don't know if there is a rocky nucleus, a very small rocky nucleus. We don't know if there's absolutely zero nucleus. It could just be a trail of dust and rocks at this point. There may be nothing left at all. And I know for a comet to be able to show up in the SDO field of view, I mean, we need certain elements in there, certain molecules, to be able to glow enough for us to actually see it. So, I mean, one of the questions is what is the material that makes them glow in SDO, and then does ISON have that? And if it no longer has that, why not? What's different about this comet? So we kind of have more questions than answers at the moment, which I know it's really difficult for the people that are watching. They think, well, you guys are scientists, you need to know this. Why don't you know this? You should know this right now. We've got so many questions, and it's going to take a long time to digest all this data. We're getting so much information about the comet. It's really been, we've been sort of drinking from the fire hose. So I'm still optimistic that we will see something of ISON in the SDO field of view soon, but it does sometimes take image processing. The pictures that go out online, they're kind of part of an automated pipeline of processing, and we have software tools that take a lot longer to run, but they do enhance a lot of the details. They enhance the contrast, they reduce sort of noise, we can pick out certain frequencies, we can enhance them so that we can see more detail. It may be that we need to do that before we see ISON in SDO, but I'm still optimistic that we'll catch a glimpse of it.
So I just wanted to kind of reiterate what Carl's saying. I think it's important for folks to know is that scientists don't have all the answers, but that's what's exciting about science. I mean, if we knew all the answers right away, then it would be kind of boring. And so this is a challenge, and this is why we do this, is because we don't really know what's going on, And unfortunately, that means that we don't necessarily get immediate satisfaction of seeing some results, but that's part of the challenge. And also, I've also heard folks sometimes say, well, you guys have to process images, and that's kind of cheating. And, well, not really. I think most people may take pictures from parties or whatnot, and they pull it up in their iPhoto or Photoshop or something, and they have to do a little tweaking because people have got glowy eyes and they're kind of washed out from the flash, something like that. And you're still getting a real image, but I don't think that's really cheating. We have the same sort of thing here. These are really, really faint signals. These are really hard objects to see, especially in a situation where we really haven't done this before. So there is a lot of processing that has to be done, and that's just part of what we have to do. So that, all in all, that makes it exciting, and that's why we stay up late and do all this work, because it's a challenge, and we're always looking forward to finding out something we didn't know and getting more questions really than answers. I think that makes it more interesting. So I just wanted to kind of add that, my 3 cents there.
There's excitement behind me as people are trying to see if we actually see a comet yet, but I don't think we've got it in SDO yet. But we will show you as soon as we do at this live Google Plus Hangout about Comet ISON. We do, however, have an image from SOHO, which Phil Plait is about to show you. Just a reminder, we are taking your questions. You may submit them using the hashtag AskNASA or ISON. And to Phil.
Thanks, Karen. I just grabbed an image from SOHO, NASA and ESA's solar observing satellite, and you can see it here. This was taken at 1748 UTC, Universal Time. Subtract 5 hours, so that's 12:48 Eastern Standard Time. And as you can see in the blue, which is the wide field SOHO view, again, you can see the tail sweeping in, and in the red, it continues in. They're not exactly perfectly aligned here, but they're pretty close. And it's not looking good for ISON, in my opinion. Now, again, this is in my opinion, and I'd like to have Carl and Alex comment on this as well. But if the nucleus, if the solid part of the comet were still intact, I would expect to see a dot. And instead, what we're seeing is a bright smear that fades into the tail to the lower right. But to the upper left, I'd expect it to just kind of stop, and it doesn't. It just kind of fades away and narrows. That's exactly what you would expect if the comet were, if the solid part of the comet were to have broken up. I'm not saying that is what has happened, because comets are very difficult to understand exactly everything that's going on in real time, but I have a strong suspicion that ISON may be an X-comet. Carl, what do you think?
Yeah, I think that's kind of my assessment too. Just before I jump into this question, so I'm looking at my own Twitter feed. You can see my little handle at the bottom there, Sungrazing comments. I'm seeing a few comments from people that say, when the camera's not on me, I'm looking sad or something. I want to tell people that I'm not, like, I'm sad about ISON, but when the camera's not on me, I'm still trying to get data, so my sad face is actually my concentrating face, because I'm trying to look at the SDO images, I'm trying to look at the LASCO images, I'm trying to get information. I promise everybody I'm wickedly excited today. This is a thrilling day for me, regardless of what happens to ISON. So, getting back on point then, yeah, I tend to agree with Phil's assessment. I was looking at that same image that he's referring to, and I am definitely worried about how the tail, it kind of narrows and it goes to a very fine point at the head. I would really have liked to have seen kind of a blob there and then the tail coming out of it, because that would be an indication there's still an active coma, there's still stuff that's outgassing from the coma, but because it's just a tiny little point, it really comes to like an arrowhead. That definitely that leaves me awfully nervous. The other thing that I want to point out in that image that Phil had up, I don't know if you guys can bring it up on screen or not, but you kind of see two tails in the comet, and there's that very thin one that's at the top, and then a sort of a more wide, diffuse one beneath. That thin one at the top, it's a beautiful image, this one. That stuff, we're pretty confident that is very heavy dust grains that have fallen off the comet. And when you zoom out on that image, I've never seen something like this before in LASCO. It's fabulous. Those big chunks of dust are sitting perfectly in Comet ISON's orbit. They're not being pushed by radiation pressure or the solar wind or anything. They are a perfect trace of the orbit of the comet through space. So that in itself is wonderful, but it does worry me that there's so much heavy material. The same thing was seen with Schumacher-Levy 9, the comet that struck into Jupiter. There was a long trail, and then along that there were brighter chunks with big fragments, but that long trail was very heavy dust. And I'm seeing this very, very heavy dust trail in the comet's tail that is that's very concerning to me. So yeah, my assessment is right in line with what Phil said there.
All right. As I've been saying, we're taking your questions live. You can comment on YouTube, Google+, use the hashtag ISON or Ask NASA. And I have a question here that I want to throw out to you. It is from SM Styles. And he wants to know, given that this has been this 50 million year trip, 50 million, 5 million, you should answer that in the question, trip to the inner solar system, how do we know it's the comet's first trip? And in answering this, maybe someone could, I'm going to throw it to starters to Carl, and anyone else can jump in afterwards, answer where this comet came from. What is this Oort cloud, whence it originated?
Okay, so the Oort cloud is basically the reservoir for a lot of the long period or non-periodic comets that we see in the solar system. So if we kind of wind back the clock a bit to when the solar system was forming, we had all this material that was starting to kind of clump together and everything. A certain amount of the material got flung right outside of the solar system. And if you imagine our solar system, we've got the sun at the center, then the planets kind of revolving around that, almost like a record, for example, and the planets kind of follow grooves on the record. Now, surrounding that record way outside of it is a sphere, a complete sphere of big chunks of ice. So they're the Oort cloud comets. And they're really right at the edge of our solar system. They're basically so far away from us that the sun's gravity can barely cling hold of them. It's just about got hold of them so they don't drift off into interstellar space. But it extends to about halfway between us and the next nearest star. So it's really a huge distance out. Now what happens is, as our galaxy rotates, so our galaxy is like a big pinwheel, we're just one little dot of junk in this big pinwheel that's spinning around. Everything's moving around, and the stars kind of move, the solar systems move relative to each other, and occasionally we'll get a star that's relatively close to our solar system, and the gravity from that star will just be enough to kind of give a nudge to some of the comets in the Oort cloud. And that's what will have happened to Comet ISON, I guess, a few million years ago or so. There had just been some sort of gravitational nudge that was just enough that it started to feel a slightly stronger influence from our sun's gravity, and then sort of started to slowly fall into the solar system. And so, so basically, that's what the Oort cloud is. It's this reservoir where all this stuff comes from.
All right, another question that has been asked by a lot of people, and I'm going to throw this one to Phil Plait, is if it survives its trip around the sun, when and where will people be able to see it from the ground with the naked eye?
Okay, that's a good question. It may be a moot point at this point, since I'm starting to be very suspicious about the longevity of this comet right now. But if it stays intact, will you be able to see it from the Earth? And the answer is, well, hopefully. As it swings around the sun, the way the orbit is lined up in the way the Earth is going around the sun, the way all this geometry works out. The best way to see it, if you live in the northern hemisphere, roughly at 40 degrees latitude, which is where I am, at least in Boulder, and where most of the population of the world is, if you go out before sunrise and you look to where the sun is going to be rising in the east, the comet should be to the north of that, so to the left, upper left, and over time it will be moving more and more north. In about a month or so, in early January, it'll actually be crossing the north pole of the sky. It's going to get very close to Polaris, so it'll be up all night. But for the next few days and couple of weeks, it would be up before sunrise. Now, what's peculiar about this is that it's also visible after sunset. And you might not think that's possible, but just the way the geometry works out, right after sunset, if you face west and look to the north, which would then be to the right, the comet will be there. But for those of us in the northern latitudes, it'll be closer to the horizon after sunset and tougher to see. So my suggestion would be to get up early and look for it before sunrise. And that is, again, given that it stays intact. With this latest SOHO image of the head all stretched out the way it is, I'm not very hopeful at this point.
I just want to let everybody know who's watching out there that we have more than 27,000 viewers right now. So a lot of comments are getting backed up. We're trying to go through questions. We've got until 3:30 Eastern Time on this Hangout, and we're going to get through some more. So keep sending them. Use hashtag AskNASA or ISON, or put them up in your comments on YouTube. But before we go to another question, I want to throw it back to Alex Young, who is a solar scientist, and one of the things people are interested in from the solar aspect is how the comets can study the atmosphere of the sun. And he wants to talk a little bit about what we're seeing with SDO on the sun per se.
So let me share my screen real quick here. Okay, so what I wanted to talk about is what exactly is the environment that the comet is seeing, and what exactly it means. So let me talk to you. What I'm looking at right now is, hold on, it's flickering. Okay. What I'm looking at right now is an image from the Solar Dynamics Observatory, 171 angstrom, so that's the wavelength of light. This is extreme ultraviolet light. This is close to X-rays, and you can see this image. Now we're pointed away from the sun a bit, but what you see when you look close to the down to the sun, just away from the edge of the sun, you see all these loops, and you see some structures that kind of curve in and then come together. We call that actually a helmet streamer because it looks like the top of a military helmet. But those structures that you're seeing are created by magnetic fields. So those are magnetic fields that are coming out of sunspots. Okay, I think most people are probably familiar with sunspots, those dark patches on the visible sun. Well, that's really concentrated magnetic field, like you can think of like a bar magnet. The magnetic field is coming out, and magnetic fields are invisible, but because the atmosphere of the sun is plasma, it's gas that's heated up so much that it loses its electrons and it becomes electrically charged, becomes magnetic material, and so it follows these magnetic fields and it traces out the magnetic field lines. It kind of looks like neon signs maybe, and those magnetic fields are where solar activity comes from, where we have huge explosions called solar flares and coronal mass ejections. And so we really want to study that magnetic field and understand it so it'll tell us why the sun is doing what it's doing. And the problem is we can study the magnetic field close to the visible layer, the visible surface of the sun, but as you move farther out into this wispy corona, it's really difficult. And normal instruments have a really hard time of studying this. So this comet, as it's traveling through, it's leaving its material, and its material is also magnetic, and it follows these magnetic fields. And this gives us an opportunity to see and study these magnetic fields in a way that we normally couldn't do with our instruments. So nature is giving us this unique opportunity to study these magnetic fields. So I just wanted to point that out because this is just really unique opportunity to study something that normally we couldn't do. And not only do we get to enjoy comet physics, but we get to enjoy solar physics all at the same time. So it's a two for the price of one. And so that's kind of my take on it.
All right, that was some of the live SDO imagery that Alex was showing us. There are comments coming in that people want to see the comet already, and of course we do too. We are hoping that somebody can spot it in this imagery, and the SDO team here in the Solar Dynamics Observatory Mission Control Center is working on seeing if we can spot it. However, we have been watching Comet ISON with a number of observatories over the last year, and one of them we got a question from somebody about the Fortis sounding rocket, and I'm going to toss to Carl Badams if he knows anything about what the Fortis sounding rocket, which launched about a week ago, I believe it was November 19th, if they got any interesting data.
Actually, it's funny you mention that because I have absolutely no idea. I'm sorry.
All right, then. Good to know. The only thing I know for what it's worth is that they were excited about their data. I don't know what they saw either. Great. Well, then, let me take another question, which I'm going to throw to Phil, though if anyone else has opinions, as always, please jump in. And the question is from Jane, it's from Jane Houston Jones.
Oh, I know Jane. Hi, Jane.
Great. Hi, Jane. And she wants to know, is it okay to try to see ISON near the sun if you are wearing your solar eclipse or Venus transit glasses?
This is a tough question because I want to be as careful as possible. Looking at the sun is not a good idea. The medical aspects of this are very complicated. Usually, if you were to just glance at the sun with your naked eye, that won't cause you permanent blindness, but you don't want to stare at it because that can induce damage. However, little kids are more susceptible to eye damage by looking at the sun because as you get older, the lens in your eye turns yellow and it doesn't let through sort of the blue damaging light. So when you're a kid, it's more damaging. But either way, you don't want to stare at it. You certainly don't want to look at it with binoculars or a telescope because what those do is they take a lot of light and collect it and focus it into your eye. So it's extremely dangerous to use that sort of thing to look at the sun. Now you can get eclipse glasses, as a matter of fact, probably sitting right here, in my desk drawer, I have a pair. These are rated to look at the sun safe. I actually cannot see a thing with these things on, so I'll take them off. And if there's an eclipse of the sun, you can use these to look at it, or you can just look at the sun normally. I use them when there are big sunspot regions, because sometimes sunspots get big enough to see with the naked eye. You can just put those things on and look. The problem is what they do is they block the vast amount of the sun's light so it doesn't hurt your eye. Well, the comet is not nearly as bright as the sun. So if you were to put on these glasses and then look up at the sun, you wouldn't see the comet at all unless the comet were as bright as the sun, and it's not. Unfortunately, it doesn't look like that's going to help much. And there have been comets in the past. Comet McNaught back in 2008 was in fact bright enough to see during the day. I went out at noon, blocked the sun by putting it behind my house, and then I could see the comet as a glowing point in the sky. It doesn't look like ISON's going to be able to do this because, like I said before, like we've been talking about, kind of looks like ISON's broken up. I'm still waiting for new data from SOHO. I don't see anything yet, but I'll update that as soon as I find it.
All right, just a reminder that you are here for NASA's Goddard Plus Google Hangout on Comet ISON. We just lost Alex, and he's off to look at the data, and we should have Dean Pesnell, the project scientist for SDO, back in a moment to tell us what we're seeing, why we're not seeing anything, what to think about that. And in the meantime, I'm going to go back to another question, which I will throw to Carl, which is come in from Christoph. And the question is, Will Comet ISON accelerate or decelerate after perihelion?
Excellent question. So the Sun is a massive gravitational force in the solar system. So as Comet ISON has come into the Sun, it has been going faster and faster. It has been accelerating at a really remarkable rate. And I believe, right around now, its peak velocity was about 360 kilometers per second, which it's about 0.2% of the speed of light. So it's a phenomenally fast object. But as it moves away from the Sun, it is going to slow down. Because as it moves away, it's going to feel that the Sun's gravity is kind of pulling it back. But it's going too fast. It's not going to get kind of pulled back and sucked back in. It's going way too fast for that. It's still going to fly off out, and it's going to go right out of the solar system, but it will gradually decelerate.
Thank you for that, Carl. I want to re-identify all the people we have here today. I am Karen Fox, here from NASA's Goddard Space Flight Center in Greenbelt, Maryland. We have in this room where I am sitting, which is the Solar Dynamics Observatory Mission Control Center at Goddard, we have Alex Young, who is a solar physicist here. We also have Dean Pesnell, who's the project scientist for that observatory, SDO. Carl Badams is talking with us from Kitt Peak Observatory, and he is with the Naval Research Labs. And we also have Phil Plait, who is the Bad Astronomer. He is a blogger on slate.com. And I'm going to hand over now to Dean Pesnell. He is that project scientist for SDO, and he's going to look at some of what SDO is seeing live right now and tell us what he sees in those images.
You're unmuted now.
And do I get to see some images?
Can you share my screen?
Hold on a sec. We are just getting those images up. But Dean, if you want to start and just tell us a little bit about where SDO is pointing and why.
Okay, so right now SDO is pointing a little bit to the left of the Sun because that's where Comet ISON path took it. We were hoping that at this point we would be seeing a glowing tail from the comet. We haven't seen anything, and we're hearing that from around the science community for SDO that Comet ISON isn't really showing up. Now, this is kind of a surprise to me because even if all of the water ice has left Comet ISON, which is what other people like to see, this water ice, even the stony material that comes off will evaporate and make the signature that we would see for a comet tail. We're not seeing that. So I'd like to know what happened to our half mile of material that was going around the Sun.
Do you think it's just a matter of maybe there's something there and processing? Do you think it's just a matter of something there that you can't see?
If there was a half a mile object flying by the Sun, we should be able to see something. But we're not. It should be getting hotter. All right, go ahead.
Well, I'm wondering, is it possible it's just if the comet itself is broken up and it's gotten smeared out so much that it's just not bright enough to see in the SDO images?
Yes,
even though it's all there, it's just spread out.
The cool thing about the SDO images is we don't see the comet as it goes by. We see the debris it leaves behind for a long time. And for Lovejoy, we saw stuff sitting in the corona for 45 minutes or so. And so the thought is that it's not watching the comet, it's watching the debris as it tries to adjust from being this very cold material to being at several million degrees in the solar corona.
But if I can jump in real quick, with Lovejoy, we know that we had a nucleus in the corona that was releasing dust and gas at the time. So it was there seeding the corona with all this stuff. with Comet ISON, we really don't know that there was even a nucleus that entered the corona. And yes, the dust sort of trail would continue along that orbit into the corona, but maybe it wasn't dense enough at that point. Maybe there wasn't enough material that was entering into the corona for it to show up.
Well, certainly if the stuff is small, then it gets affected by the magnetic field, and it doesn't make it to perihelion. It just it gets attached to a magnetic field and leaves, so we don't get to see it. But it would all continue to evaporate as it moves in towards perihelion. So it's if we had a substantial comet at some point, it's kind of surprising that it would all evaporate. Even if it did start breaking up, you would think it would take a while for it at least to evaporate as it moved in towards the sun. But,
well, so I was going to say, isn't it? My understanding was that it was mostly, you were seeing a lot of ionized oxygen in SDO for Lovejoy, correct?
that's right. And you get oxygen from water ice or from virtually any asteroidal type material, and from any hydrocarbons. So if anything got into the perihelion point and started evaporating, we would expect to see some sort of signal from that.
We should see something. Okay.
Yes. That's why I kept saying if it breaks up, it doesn't matter. It just makes a better signal for me. But now it's broken up, and I didn't see anything.
And I have a question to throw at Dean while he is here. It is a question from @SouthScanner. And he's saying, as you've just been talking about breaking up and what's going on, is it possible the comet is intact but just not outgassing anymore?
It would have to be essentially solid iron at this point to not outgas, and even that would become fairly quickly hot enough to start molecules coming off of it. It's in an environment where it's going to be heated up to several thousand degrees, and anything we know of is going to evaporate. And also iron, these things tend not to be a kind of a concentrated core. They tend to be, bits and pieces, and so it would fall apart rather than have a really solid core that would be able to move through the sun. But any kind of material that moves this close to the sun will heat up quite substantially.
Well, thank you, Dean, for showing us a little more about what's going on in SDO. I know Phil Plait has downloaded a latest image from SOHO, which is, I keep on calling it SOHO, but let me tell you what that stands for. That is the Solar and Heliospheric Observatory, which is a joint NASA and European Space Agency mission. And so he's going to show us the latest picture there.
Well, this isn't the latest image. This is the latest one I have access to. The NASA SOHO site, oddly enough, is getting slammed by people trying to download all the images. But there are other sites that have some of the images. So I have this one from 1812 UTC. So again, subtract 5 hours. I want to do this out loud to make sure I do it right, which is 1:12 Eastern Time. And as you can see in the picture, again, in the wide field picture, which is in the blue, you can see the two tails of the comet. In the red picture, which is also from SOHO and slightly narrower, the trail looks like it's fading compared to what it was like before. However, you got to be careful. There's also some activity there on the right. That's the sun, a little bit of solar activity, a little bit of, magnetic activity. The sun blowing off some particles. When that gets bright, the image compensates for that and makes everything else look dim. So it's hard to say exactly if the trail looks dimmer. But it looks that way to me. It seems to there's a bright smear, and then it fades out as it gets closer to the sun and gets narrower. That's for sure. And it again, it really looks to me like this thing is broken up. And I'm seeing a lot of other people saying that on Twitter as well from other observatories.
Great. Since we just saw some lovely imagery from SOHO, Alex Young wanted to jump in and show us some imagery from some of the other observatories that are watching ISON, namely STEREO, that's short for the Solar Terrestrial Relations Observatory, which is a NASA mission that watches the sun, as well as perhaps some Proba data, which is a European Space Agency mission. Once we get the STEREO image, Carl, who works intimately with that, might also have something to say.
Okay, so let me Okay, so I've pulled up a stereo image, so now perhaps Carl can speak to it. This is from the Stereo Ahead spacecraft.
Yep, so I guess the first thing I would say is that people are probably looking at that and thinking, well, that's a pretty crappy looking image considering what we've just been looking at. But that's a low resolution image from the STEREO spacecraft. I should just take a second to explain the way the STEREO spacecraft work. There are actually two spacecraft, and they were launched in 2007. Right now, they are on the opposite side of the solar system from the sun, from the Earth. So they are looking back at the sun, and they can see the Earth like in the distance on the far side of the solar system. So they're a long distance from us. And the further a spacecraft is from us, the harder it can be to get data down from that spacecraft. It takes longer, it takes more sort of power to pull the images down. So we don't get a real-time feed of high-resolution images from stereo the way you're seeing with SDO, for example, and for SOHO. Instead, what we do is have a constant stream of very low-resolution images that comes from that satellite. So what you're seeing there, if you guys can bring that back up, because you've switched to LASCO again. So what you're seeing in that image is a low-resolution coronagraph image. Obviously, Comet ISON is very obviously visible in that image. Can somebody bring it up? Maybe not. I guess they're not listening to me.
Everybody's running around trying to do a million things at once here. There's so much
I guess so. I'll just talk to the 32,000 people that are watching us right now instead. So
we're trying to get a stereo image back up for you, Carl.
Okay, thank you. I'll just keep chattering away. I'll just keep everybody occupied for a few minutes. So what we're seeing in that image anyway when it comes up is Comet ISON from a different perspective in space. But it is a coronagraph image, so it's like the LASCO image that Phil has been showing, like you're seeing on your screen now. So it has the disk in the center that blocks out the direct sunlight so that enables us to see kind of the fainter stuff that's going on around the sun. And because the spacecraft is on the other side of the solar system, you see the comet looks like it's coming in at a different angle. Now these images are going to be really useful for us in modeling this dust tail. Specifically that trail that I was talking about earlier. We still see it right now on the image we got on the screen. There's kind of the two tails, and there's the very thin, more dense tail along the top. That dust trail, that's very interesting. I've really not seen anything quite like that in the LASCO images before. So hopefully we're going to get to see that as well from the stereo satellites, and because of their position in space, we essentially get stereoscopic views of that. So we hopefully can build up a really nice 3D picture of what's going on with the comet tail. Beyond that, there's not much more I can say about that stereo image. Firstly, because we still can't see it, and secondly, oh no, I see it on Alex's screen. Okay. Secondly, it's low resolution, so there's really not too much that we can say right now.
All right, I want to talk a little bit about other comets. For one thing, we have a video that's just been put up on Comet Lovejoy, and maybe Alex or Phil can speak to what we're seeing in that image and SDO, but I also want to add on a question that @Dwayne Briers has sent in, which is, with ISON's fate looking bleak, when is the next big comet due?
That's a good question, isn't it? It's hard to say. There are actually 4 or 5 comets up right now that are visible through either binoculars or a telescope, including Enki, and I'm not even sure what the other ones are. There's a Lovejoy up right now, too. Lovejoy is actually the name of an astronomer who has discovered 4 comets, in fact. And so you never know when there's going to be the next great comet. Sometimes something looks really good, when it's out, past the orbit of Mars and Jupiter, it looks like it's going to get bright. Then by the time it gets close to us, it fizzles away. That happened with Comet Kohoutek in the 1970s. Other times, like with Hale-Bopp or Yakutaki back in the late 90s, those were spectacular, easily visible to the naked eye at night. Hale-Bopp was astonishing to go out, just look up and see it with the tail streaming out. It was gorgeous. So you never know what's going to be the next big comet. They come in from the outer solar system sort of semi-randomly. So it could be later in 2014, or we may have a surprise where one comes in and gets very bright sooner than that. Or it could be years. We'll just have to wait and see. But this is ISON is a. I want to say this because I think it's important. I'm seeing on Twitter a lot of people being very disappointed that ISON is broken up, and I can understand that because if it remained intact, we'd be able to see it by going out and looking for it in the next couple of weeks with the naked eye. If it's broken up, and I really think it has at this point, that probably won't happen, so that's disappointing. On the other hand, the fact that it's broken up is really cool. There's a lot we can learn from that. We'll get a lot of data from this. Because it's broken up, that means it will release all of the materials that were inside it. We might be able to study that stuff and learn more about comets. This thing came from the outer solar system, which probably has remained untouched for 4.5 billion years. So this is a time capsule. It's a time machine looking back to the birth of the solar system. We can learn a lot from it. Plus, it's just cool to think that it passed that close to the sun and got destroyed. That's really neat. So I can understand people's disappointment, but on the other hand, science is science. Reality is reality, and if we can learn from this, that's good news.
And I just want to jump in real quick to add to what Phil said and address the original question about when will we see the next comet. One of the really fantastic aspects of Comet ISON is we've never seen a comet like this. Because it's from the Oort cloud, it's a dynamically new comet. It's never been to the inner solar system before. That aspect of it makes it, not completely unusual, but not every comet we see comes from the Oort cloud. So we see Oort cloud comets from time to time. Okay, fine. But ISON is also a sun-grazing comet, and we see sun-grazing comets all the time. The SOHO satellite actually sees a tiny sun-grazing comet every 2 or 3 days. So, okay, sun-grazing comets aren't that unusual either. But we've got the combination. We've got an Oort cloud comet that's in a sun-grazing orbit. That is something that we have never seen in modern recorded astronomy. So it's probably happened in the past. I'm sure it's happened in the past, but we have no modern astronomical record of an Oort cloud sun-grazing comet coming in. So this is a spectacularly rare event. Rare to the point that we've never seen this before. And we have no idea when we're going to see something as amazing as this again. And I completely agree with Phil that science is science. We can't control what a half-mile chunk of ice is going to do when it flies through the million-degree corona at 0.2% the speed of light. We've got no control on that one. There's some pretty awesome stuff that's going on at work that we really don't have a hand in that. It's going to do what it's going to do. And at this point, I do suspect that the comet has broken up and has died, but ISON has surprised us a lot over the past few months, so let's at least give it a couple more hours before we start writing the obituary.
Great. Let me take a moment to remind everybody what we're doing here today. This is NASA's Google Plus Hangout on Comet ISON. Right now, Comet ISON is making its slingshot around the sun, what we call perihelion, its closest approach to the sun. We're taking people's questions on YouTube, at Google Plus, and also via Twitter using the hashtag ISON and Ask NASA. We have a lot of questions. We are trying to get through them. We have with us at the moment Carl Badams, who is with the Naval Research Labs, and he is joining us from Kitt Peak Observatory. I don't know that we're going to have him for much longer, but he and Phil Plait have been joining us. Phil Plait is the bad astronomer at slate.com, and he too is probably going to have to part fairly soon. I have a question for Carl before we lose our scientists, and that is from @BlairNemo. He is asking, So often we are told that comets are balls of dirty ice, but where does the water actually come from?
That's a good question. That I'm not a planetary geologist in the sense that I study those things, but basically comets are, as we've said before, they're a collection of the material that built the solar system, and it's really just about the abundances of the elements that were floating around when our solar system was just a big flat disk of dust and stuff floating around, and bits started to hit each other and stick together. It's really just a consequence of the composition of the solar system when it began, that they tend to be icy, and I think there's maybe a little bit more to it than that, but I'm not an expert in that aspect of comets, so I don't want to start getting into speculation of deep water.
Well, no, you're on the right track there. That's correct. These comets, especially something like ISON, formed with the original solar system 4.5 billion years ago, and there's a lot of material out there. When a star forms, it forms from a cloud of gas and dust and material, and there's a lot of elements in there: hydrogen, oxygen, silicon, things like that. And the hydrogen and the oxygen are very attracted to each other, and they form H2O, water molecules. And if they're close to the sun, that stays a gas. When it's farther away, it freezes and becomes an ice. And so a lot of these things, out past roughly the orbit of Mars, Jupiter, that area, you start getting the frozen particles of water ice sticking together. They form giant clumps that form the nuclei of these comets, and they can get flung away to the very distant outer solar system by Jupiter's gravity. So we have this population of these things way the heck out in the outer solar system, way past Neptune's orbit, and occasionally they drop in like ISON is doing. So that's where the water comes from. It comes from the origin of the solar system. And in fact, there's still a raging debate in astronomy right now over whether the Earth's water itself formed here or was brought in from comets. I suspect it's a little of both. So that's what makes up most of these comets. It's rock, gravel, and dust mixed in with this water ice that is from the early solar system. And when the object comes in near the sun, the ice turns into a gas and forms that fuzzy head, the coma, and the tail streaming away. And it's not just water. Some comets have frozen carbon dioxide, frozen carbon monoxide, ammonia, and a lot of other things that can also basically sublimate is the term, turn directly from a solid to a gas and form the comet's fuzzy head.
Great, thank you, Phil.
And I'm going to jump in again. And one more thing. I'm glad my friend Alan Boyle, a journalist for MSNBC, has tweeted and reminded me that sighting Spring is a comet that's going to pass very close to Mars next year. It's not going to hit it. There was a possibility a while ago that we thought it might. It's just going to miss Mars. But the material surrounding the comet is so large that stuff might sweep past the planet. It's something that astronomers and planetary scientists are keeping their eyes on right now.
Thank you, Phil. Behind me in the Mission Control Center at the Solar Dynamics Observatory Mission Control Center here at NASA Greenbelt Space Flight Center in Goddard, Maryland. Oh, no. NASA Goddard Space Flight Center in Greenbelt, Maryland. I've been saying that a lot of times already today. We have people trying to pull up imagery of SDO. I'm going to take a moment to show what we can currently see in the SDO images. The sun looks beautiful. Unfortunately, we're not seeing Comet ISON yet. Do we have that up? Oh, we do have it up. I just can't see it. So one of the things that's been happening today is SDO has been pointing at 3 separate places. We call this off-pointing because they're not looking right at the sun. And you can see now that the sun is a little bit off to the right in this image. We have the solar atmosphere, the corona, sweeping around to the left. And that is where we are hoping to see Comet ISON. Haven't seen anything yet. We are taking your questions live, and I have another one to throw out to Phil Plait and Carl Badams, who are still with us, and we'll have some other people joining us again later. For now, the question is, it's from Suraj Biradar, and the question is, how big does a comet have to be to break up or not break up, provided, you know, within the same kind of distance from the sun?
Ooh, that's interesting. Carl, do you have something for that?
Yeah, I can. Yeah, I'll take this one. The answer is it's a little bit complicated. One of the main driving factors on whether a comet will break up or not is how close it gets to the sun. So it can be really huge, but if it gets really close to the sun, the sun's gravity is going to rip it to pieces. And likewise, it can be pretty small, but as long as it's far enough away, then it will be okay. And just to elaborate a little bit on that, so the closer a comet gets to the sun, remember the sun has got just an extraordinary gravitational pull. It's really insanely strong. As a comet or an asteroid or whatever goes past the sun, the side of the comet that is closest to the sun actually starts to move at a different speed than the side that's furthest from the sun, and that kind of is like a shearing effect. It essentially elongates the object. And comets are not structurally strong. They're a fairly loosely packed ball of ice and junk. So their density is kind of like a good-sized snowbank or something, a well-packed snowbank. That's sort of typically how dense a comet is going to be. So they can't withstand too much of this stretching. But as long as they're far enough away from the sun, then they're going to be okay. But if they get too close, then that's obviously going to really stretch them. And the smaller they are, the higher the risk of breaking up. And that's because there's a secondary effect that we have to take into account, and that is the solar radiation. So the sunlight that is hitting the comet is causing its surface to boil away furiously. And Dean described earlier that the comets basically sweat, and that helps to keep them cool. And that is indeed the case, that the vaporizing material sort of carries some of the energy away, so they don't completely vaporize instantly, but still some of that radiation will sort of propagate a little bit into the surface of the comet. And if there happens to be any weak points in the comet, like a structurally weak point, if the wrong bit of ice starts to melt or whatever, it can expose a fracture or a weakened area of the comet, and then you couple that with the gravitational stretching, and it's going to fall apart. And so we've got lots of complicated models that try and predict a comet based on how big it is and how close it is to the sun, as to whether it's going to fall apart or not fall apart. And Comet ISON has been frustrating in so many ways, and sure enough, it was frustrating in this way as well, because when we used our models, and it was my colleague Matthew Knight that did a lot of work on this, when we used our models for whether ISON would break up or not, he found that it basically sits right on the line between yes and no. So it sat perfectly on the maybe line. And I think at this point we know which side of the maybe it fell, but it's a complicated process.
Right. I actually don't think we've mentioned it very often, but the nucleus of this comet, ISON, is roughly 2 kilometers across, about a mile. And that's an upper limit. It's hard to say exactly how big it is, because what you've got is a solid chunk, which is called the nucleus, and then that is emitting the gas, which is then enveloping the solid chunk, and that's called the coma, which is Latin for hair. Not anything I might happen to know about, but there you go. And as that stuff evaporates away off the comet nucleus, it gets very thick, and you can't see the solid part in there. And the solid part's typically very small. So from millions and millions of miles away, it's too small to be seen even with a big telescope. Well, Hubble observations, which were taken fairly recently, they looked at ISON and were able to give an upper limit to how big it is, because if it were bigger than 2 kilometers or so, they would have been able to see that in their images. It would have looked like an extended object. Since it was only essentially 1 pixel across. It's more complicated than that, but that's essentially what they saw. They knew that at its distance, it couldn't be any more than about 2 kilometers across, so it's tiny. Hale-Bopp in the 1990s was 30 kilometers across, 20 miles. So that's really, really big. These things are all different sizes, and that all plays into whether they can survive or not as they pass near the surface of the sun. Now, actually, Karen, if you can put up that picture of the
picture of the dates?
Yeah.
I think it is up now. We've got it up.
Okay, great. Hopefully what you're seeing here is an animation that shows a sort of a cartoon of the horizon, and you can see it after, let's see here, is this, let me click on it. This is in the east-southeast sky before sunrise, and the position of where the comet should be after this week. So on December 1st, right before sunrise, it's very low, but as time goes on and the comet moves around the sun, it'll be higher and higher in the sky. Its location, its actual physical orbit around the sun, combined with the Earth's motion around the sun, make it arc away to the upper left, which is towards the north. Now, mind you, this is for people in the northern hemisphere. If you're in one of these stand-on-your-head southern hemisphere places like Australia or South Africa, a place like that, this will be reversed. You'll see it arcing off to the right. That takes a lot of getting used to. I've been to Australia a couple of times, and seeing Orion upside down or the moon pointing the wrong way is very strange. But this is for Northern Hemisphere viewers, and again, you know what? This is only if ISON has survived. And again, on Twitter, I'm seeing a lot of Monty Python X parrot jokes right now, and I have to say, I'm kind of agreeing at this time.
Well, that's a perfect lead-in to talk a little bit about sun-grazing comets in general. Sungrazer is a comet that goes close to the sun, and we have been introducing Carl Badams as a comet scientist, but we've not mentioned the fact that he really works with these sun grazers a lot. So I'm going to throw a question to him. We have a question in from @MRK Tracy, and the question is, how often do comets die as they go around the sun, and what happens to the pieces? Is there a chance the pieces might make it back?
That's a good question, and we see comets die all the time, and this is a new discovery that we made, newish anyway. In the past, like 15 years or so, the SOHO satellite that everyone has been watching carefully today, it was launched in 1995, and since then, it has actually discovered over 2,500 new comets. It's more than doubled the number of comets that we have on record, but these comets they're very tiny. They're maybe sort of tens of meters or so, kind of like a small to big house size objects, and we only see them for a few hours at a time, right before they completely vaporize. But we see one on average, about every 3 days. It depends on the time of the year because of the particular orbit that these comets follow. Most of them are part of one continuous stream of comets. It's what we call the Kreutz group of comets. It originates back to a massive sun-grazing comet that probably a couple of millennia ago went past the sun and completely fell apart, but not to the point that ISON perhaps probably has done. But it fell apart into a couple of smaller chunks, and then a few hundred years later, these smaller chunks went past the sun and they fell apart again into much smaller chunks. And long story short, we have this long stream of very small comets that go through space and they fly into the sun. About every 3 days, we see a tiny one that goes in and it gets vaporized. So this happens all the time. As for what happens to the material, I mean, obviously, if no parts of the comet survive, then there's nothing to return. But the material will sort of go into the solar corona, and eventually it will get blown out in the solar wind. And I guess Dean isn't on right now. Maybe Alex can talk about this a little bit, but it's my understanding that one of the things we were interested in with ISON is maybe if it does sort of fall apart and deposits all of this material in the solar corona where it's vaporizing, this material eventually will get pushed out in the solar wind, and we may be able to detect it out at spacecraft far from Earth. So do you have any comment on that, Alex? Is that something you're familiar with?
I don't know a lot more about it than that, but basically you summed it up. You know, we have several different spacecraft that monitor the solar wind, and you know we see larger elements, oxygen, things like that in the solar wind, and it tells us a lot about the sun generally and the environment in the atmosphere. And now, if Comet ISON is depositing this material and it's being swept out, then that gives us an opportunity to study that with some instrumentation which is normally not focused on that. So yeah, it's a unique opportunity to perhaps sample, do a little bit more exciting chemistry at a distance, I guess.
And that was Alex Young, who is a solar scientist here at NASA's Goddard Space Flight Center in Greenbelt, Maryland. He was with us earlier. He is back joining us again, and he also has some additional observations he wanted to show us. We are sitting here today for this live Google Plus Hangout in the Solar Dynamics Observatory Mission Control Center, and our hope was to show live imagery of Comet ISON as it made its slingshot around the sun. And we're seeing great pictures of the sun, but we're not seeing ISON. So he has pulled up some other images from Proba-2, which is a European Space Agency mission, and he's going to talk about those.
Yeah, I just wanted to give a sort of a quick shout out to my colleagues at the European Space Agency. You know, they have a mission called Proba-2, which has a special instrument called SWAP, which looks at wavelength much similar to what we're looking at when we looked at the golden images from SDO. And SWAP is kind of cool because it sees a little bit farther out away from the sun than SDO does, but it also observed the Lovejoy comet just like SDO did. And so the folks in Europe decided that they would also do an off-pointing, much like what SDO is doing, to try to see it with the Proba-2 spacecraft. Now, in this case, unfortunately, we don't have any data more than, you know, if SDO doesn't see it, then the chances are that Proba-2 is not going to see it. But I just wanted to pull up a quick image just to show you what it looks like. It is some pretty nice data. They did have some great observations from Lovejoy. And I just wanted to give a shout out to them, and you know, hopefully we'll all get lucky and something will show up in the data.
Thank you, Alex. Just wanted to let everybody know that some of our participants will be leaving shortly. Carl Badams, who has been joining us from Kitt Peak, he is a researcher at the Naval Research Lab. He works a lot with solar observatories and sometimes with comets as they go near the sun-grazing comets. Carl, anything you want to let us know as you say goodbye before you go?
Well, I guess the tone here hasn't been we've been talking excitedly, but it does seem that Comet ISON probably hasn't survived this journey. I did just take a look at a recent LASCO image, and I'm looking at it right now, and I'm not seeing anything that emerged from behind the occulting disk, the solid disk, and that I think is that could be the nail in the coffin there. So I'm delighted to leave you all on such a happy note with a bear of such good news, and then run out and leave you to drown your sorrows maybe. But this has been it's been an amazing journey. I've had an extraordinary time. It's been the busiest year of my career, and this comet really has sucked away an extraordinary amount of my free time, as my poor family will attest. But and I know it's sad that it seems to have ended this way, but we're going to learn. We have learned so much. We're going to learn so much more about the comet. This has really been an amazing astronomical spectacle, and so I hope that everyone appreciates just how amazing this has been.
Thank you so much, Carl, for joining us today. We will be in touch.
Okay, bye guys.
And as Carl walks out, we have Dean Pesnell coming back to join us. He is the project scientist for NASA's Solar Dynamic Observatory, and he is sitting in the same camera with Alex Young, who is also a solar scientist here. Just a reminder, our other participant, maybe you guys could mute your microphone for a sec, thanks. Our other participant right now is Phil Plait, who writes the Bad Astronomer blog at slate.com. He's going to be with us for another 10 minutes or so, so if you Phil may jump in and give his last comments as well. A reminder, we are taking live questions on YouTube, on Google+, and via Twitter with the hashtag ISON and Ask NASA. But before we go into another question, I will hand it back off to Dean and Alex to tell us, about these really pretty pictures of the sun, but not Comet ISON, that we are seeing in SDO.
To actually see Comet ISON in the SDO images today, we've moved into our third pointing position, and that was the one that was the longest shot, because it was the comet had the most time to evaporate before it got there. And the fact that we haven't seen it in the first two really means that whatever made it into this part of the orbit is not showing up along the SDO images. We're pretty sad that we didn't see it, but we had a good time trying to set all this stuff up, and it's always nice to show that SDO can get your data quickly. So that's what we did.
Dean, while we have you here, I would love to ask you a little bit about seeing comets and SDO in general. I know that when it first went up, that wasn't really the point, but maybe you can tell us about the comets you have seen and what kind of science was learned about the sun by the comets.
Sure. We've seen two comets in SDO. Both are sun grazers. We'll probably never see anything but a sun grazer, because when we see a comet, we don't actually see a comet tail, which is dust and other things that come off the comet and reflect light from the sun back to us. We actually see things glowing inside the corona of the sun. So you have to be close enough to the sun that can happen. And we also only see oxygen. We don't see any other element in our telescopes. This was a surprise when we set out to explain why we see anything, but it looks like it's been shown fairly definitively that we see essentially only oxygen from the comet. This made us happy because comets are about 40% of the atoms that come off a comet are oxygen, and so that means that whenever a comet goes by, we have a pretty good chance of seeing it. In the case of Comet ISON, it appears to have disappeared and broken up into small enough chunks that over the course of hours or a day or so, that those chunks have all evaporated. And once it gets small enough, it sees the sun's magnetic field, and then they just move away, and they get off the trail of the comet, and more importantly, they don't stay together, and then we don't get to see them. They really have to kind of stay together as they go along, and we didn't see that. So we're going to learn a lot about how comets don't work around the sun. I guess that's our next goal. I hope we see another one pretty soon, maybe soon.
I hope so too.
I guess that's we keep looking. We have people in in the room next door here that are going in and trying to tease a small signal out. If the comet indeed did break up and evaporate, our best chances of seeing it would be early in the in what we call the approach pointing. That would be the place where we would have the best chance of seeing it.
Thank you so much, Dean. We have one last question for Phil Plait, who is unfortunately going to have to leave us soon for his Thanksgiving meal. But one question from @Brendan Loy, who is asking a question on behalf of his wife, who is @MileHighBecky. And the question is, why are stable orbits even possible? Why doesn't the International Space Station crash into Earth? Why doesn't Earth crash into the Sun or ISON into the Sun?
Well, this was a question Isaac Newton asked himself, actually. How is it the moon goes around the Earth? And he formulated his rules about gravity based on that idea. The idea is that if you were to have just the Earth and something out here, the gravity of the Earth would just draw the thing in and it would just fall straight in. But if you could give that thing a little bit of a sideways kick, it wouldn't just go straight in, it would actually sort of arc in. And if you could give it more of a kick, it would go around the Earth even more. And if you could actually give it enough of a sideways speed, it will actually fall toward the Earth at the same rate that it's moving away or to the side of the Earth, and you get a circular orbit. It's always falling, but never actually hitting the Earth. That's why astronauts in the space station, for example, feel weightless. It's not that they don't have weight, it's that they're in free fall. They're just falling all the time. Douglas Adams wrote about this in Hitchhiker's Guide to the Galaxy, that the secret of flying is to throw yourself to the Earth and miss. And that's basically what satellites do. And there are a lot of different kinds of orbits. You can have a circular orbit like the space station does, more or less, or you can have highly elliptical orbits, or even ones that are open-ended, parabolic and hyperbolic orbits, like ISON had. And you know what? I'm just going to go with past tense here. Basically, the debris, I suspect, from ISON is flying past the sun right now, and will probably, it could probably exit the solar system. It'll just keep going forever, because the kind of orbit it's on, it's moving sideways, basically, faster than it's moving toward the sun. The sun's gravity could not hold on to it, and it's going to fling it out into interstellar space. And that's why we have orbits. And in fact, Carl mentioned in the SOHO images, we still see the tail of the comet coming in toward the sun, but we haven't seen anything coming out. And I don't know when we should expect to see that. It's, let's see, I'm 7 hours past UTC, so it's almost 2,000 hours there now. And I would expect that if the comet had survived, we should be seeing some of that stuff coming around the other side. I don't have the latest images from SOHO. The latest ones I have are still from over an hour ago. So I don't know, but I again, as we've been saying over and over again, I don't think the comet made it.
Phil, thank you so much for being with us today. I really appreciate your taking time out of your Thanksgiving day for this exciting perihelion, even though ISON, as you say, may already be in the past tense. Thanks for being with us. This was Phil Plait, the Bat Astronomer from Slate.com, and we'll say goodbye to him today. Happy Thanksgiving, Phil.
Thank you all very much. Have a good holiday, and I hope we still learn a lot from this event, even if the comet didn't quite make it around. But thank you very much.
Great. And with that, let me remind everybody, I keep talking about the Solar Dynamics Observatory Mission Control Center, that's where we are at NASA's Goddard Space Flight Center in Greenbelt, Maryland. But I think we should talk a little bit about what the Solar Dynamics Observatory is. It is, in fact, up in space, and here to tell you a little more about it is Dean Pesnell, the project scientist for SDO.
Right, thank you. Okay, of SDO, but I'm going to use one that's more fun. We have a Lego model, and it has, this is SDO, looks like this. It has a big flat surface in the front, has a couple instruments, has the HMI instrument, the Eve instrument. And then it has the 4 telescopes that we've been using today that are called AIA, or the Atmospheric Imaging Assembly. Each one of these telescopes takes pictures at different wavelengths or colors, and then we send them to the ground and we put them in a database so we can study the sun. Now what we really are studying is how the sun makes a magnetic field. And the images that we look at show all these really cool looking loops and whirls that are that magnetic field being lit up by material from the sun. Today, we took this telescope, and instead of pointing it at the sun, we pointed it just a little bit away from the sun to try and look at the comet as it went by. The Eve instrument, it looks at the sun as a star, and the comet probably wasn't going to affect it no matter what. HMI actually was running to look for the comet as well, and when we spoke with the people that run that a few minutes ago, they said they had seen nothing either in the HMI instruments. So in general, we're always pretty happy to try and do some new science with our telescopes and our satellites. We would like to, actually see the comet the next time, but all in all, we think that it's worthwhile to look for these new things. They teach us new things about comets. They teach us new things about the sun, and that's why we're here. So thank you, Karen. That's the SDO.
Thank you, Dean. I want to follow up on that with a question.
Okay.
I'm going to have you mute your microphone for just a second, though. A question about studying the sun. We have a question here from @AugustPim, and he wants to know, we're talking about ISON and using ISON to study the sun. Is there anything that can get close enough to the sun to study it? Any spacecraft we could send to do that?
Okay, well, we are sending a spacecraft to the sun. It's called Solar Probe Plus. It will not get as close to the sun as the sun-grazing comets do, because the heat is a real problem. But almost as important is you actually can't talk to the satellite when it's that close. You need to somehow maintain radio communications. So you have heat, you need to be able to talk to it, and also it's actually difficult to make measurements at these temperatures when you're in space on a satellite. So we send it not quite as close, but we're trying to get about 10 solar radii from the sun, whereas Comet ISON went into a little less than 3. So we're out a little bit further from the sun, but we're as close as we can with this first spacecraft. And then once you send one, then that tells you what you can do the next time. So you have one that goes through, and it makes it through, and it makes some nice data, and that comes back, and the engineers and the scientists sit down and they say, oh, that worked really well. We should be able to go even closer the next time. So each time we would be able to send something a little bit closer. So look forward to Solar Pro Plus going up later this decade, and then we'll see what we can get after that.
Thank you again, Dean. I have a comet question for you now. It is a question from @Telluric, or Rusty of Silicon Valley. And the question is, as the comet is going around, does the loss of mass of the comet impact the orbit?
So as the comet's going around the sun, it loses mass. It tends to come off kind of in all different directions, and it affects it a little bit, but actually not very much. There are other things that happen that are more important, like it breaks up. And if it breaks up, then those things will have a little bit of velocity, and they'll move apart, and that affects the orbit. And we see that in some classes of sun-grazing comets. The effects of the jets is relatively small, but it can be seen in some of the comets that come around again and again. You can actually see their orbit change a little bit.
Thanks so much, Dean. I'm going to remind everybody what we're doing and why we're here today. This is a Google Plus Hangout, a NASA Google Plus Hangout on Comet ISON, which right now is making its closest approach to the sun, which we call perihelion. And there have been a number of NASA observatories which have been watching it, and one of them is the Solar Dynamics Observatory. We are in the Solar Dynamics Observatory mission control room right now with a number of NASA scientists trying to figure out what we can see of the comet. So far, nothing in SDO, but maybe our two solar scientists who are sitting with me right now, they are Alex Young and Dean Pesnell. Alex, maybe we could do that again. Alex Young. That one. Dean Pesnell. That one. Are sitting with us, and maybe they can talk a little bit about what we've seen over the last few days, because other solar observatories have been watching Comet ISON. So tell us what we've seen lately.
Do you want to start off?
Well, this morning I got up and was watching the images from the SOHO LASCO spacecraft, and they actually looked pretty promising when I first started looking at them. The comet was nice and bright, and then as it got closer and closer to the sun, you would expect it to continue to get brighter and brighter, but unfortunately it got dimmer and dimmer as it got towards the sun. Other satellites such as STEREO have been watching it a little bit longer because just the way they look at the sun, they can see it. And here's a nice little movie, and you can see Comet ISON.
Let me turn this on, screen share, so we can see this.
So we have some instruments on STEREO that are kind of like wide.
Oops, that was a mistake.
Oh man, did you share that screen, Alex?
I did not mean to share that screen.
Wow, well, share it again. That was.
Sorry about that, folks. That was a little bit of a. Yeah. Let me share a different screen and actually put the video up so you can see it. All right, so let's make this a little bigger.
Earth and Mercury, right?
Okay, there we go. So here we have two comets that are moving towards the sun. The smaller one in front is called Comet Encke, and that's a comet we've seen before. And then the larger comet coming in from the left is Comet ISON. You also can see two planets, and I always get these backwards. It's Mercury is the little one.
That's moving faster.
Yeah.
And the Earth is the brighter one.
Yeah.
And these movies look kind of funny because what they actually are is they take the frames of the movie and they take the difference so that you get rid of some of the noise, and things that move stand out a lot better. And you can really see, coming in from the right, you can actually see some solar wind coming in. That's probably a little CME flowing from the right to the left. And that's really what these are designed to look at, is those small ripples in the solar wind. But they also pick out comets and the planets as well, and stars in the background.
Right. And maybe shortly after this, we'll show some old Encke images with the CME going past the comet.
You know, actually, when we were talking about this event the other day, the thing that I thought would be really cool would be if a CME had gone off and we had a nice tail from Comet ISON, if a CME had erupted, and we could have seen the interaction of that, the comet material with that CME as it went by. That would have been nice to see. Next time.
Next time.
So now that we have talked about where we can see it and where we can't see it, and that perhaps it has not made it around the sun, I'm going to ask the question that a lot of people have been asking, and which indeed one of our colleagues here at NASA just asked. This is a question from Rebecca Roth, and she wants to know, if it's really broken up, are we going to be able to see it in the sky in December?
I would say probably not. If we don't see it coming out from behind in STEREO, in the SOHO images, the chances of it being bright enough as it moves away from the sun is quite small. I mean, those are really good detectors of comets, and if they don't see it, we probably won't. That really says there's nothing there.
Let me ask you one other question, since we've been touting you as the solar scientist here today, and Alex Young, solar scientist. And tell me, why do solar scientists care about comets going near the sun? What can we learn from the kinds of things, the kinds of explosions the sun can put out by using a comet to study the solar atmosphere?
Where's the Lovejoy picture? The Lovejoy movie.
Can you guys somebody show the Lovejoy movie?
So a couple of years ago, we had one of these comets go by the sun, and we set up to watch it because we didn't know what we were going to learn. We had seen one before, and it had disappeared before we could figure out what we could learn. And then Comet Lovejoy in December of 2011 came around the sun, and we did an event like we did today where we set up the data so that people could look for it. And it was actually quite a nice comet. We were really pleased. We saw this really nice tail, and then when we pointed back to normal solar pointing, we saw an even nicer tail. So now when we see these, we realize that the reason the tail looks so interesting is because as the comet goes by, it sees the sun's magnetic field, and the material from the comet jumps up and down in the sun's magnetic field. So some of it goes one way and some of it goes another way, and that's telling us about the sun's magnetic field. And that's a place in the corona where we have a hard time measuring the sun's magnetic field. So if now all of a sudden these comets can tell us what's going on, just the direction at first, and then maybe we could figure out how strong it is. That's pieces of information we can use to better understand how the sun makes a magnetic field. And then as we get more into it, why is it bright was a pretty good question, because we didn't quite understand why cold material coming off would be bright. It should be dark because of our way things work. And it wasn't. It was bright. And so that meant that there was something else happening as well. And that's when we found out that oxygen was a really good probe of what was going on in the corona. And then that allows us to know that anything we see glowing is probably oxygen, and we can study how that oxygen gets hot. And then the third thing that we would like to look for, and this is what I really hoped ISON would do for us. ISON was going to put material into a place very close to where the Earth orbits around the sun. So it would come out and along the same plane that the Earth goes around, and we might actually be able to measure this material when it gets out to the Earth, or to when it goes to the two STEREO spacecraft, which are around behind the sun. So if we could measure that material when it gets out to another spacecraft, that would tell us how the solar wind is pushed away from the sun. Because all of a sudden, it's like you put a bottle in the ocean, and when you pick the bottle up somewhere else, that tells you about the ocean currents that took that bottle from one place to another. Putting these weird ions into the solar wind would tell us how they got from here out to where we made their measurement. I don't think we're going to see any of them either.
No, yeah, it doesn't seem like it.
But so we have a couple of things, and we're still kind of being creative on what we can use these comets for. First, we'd like to see a couple more of them in our measurements, but we do have nice ways that we can use these comets to study the sun. And the nice thing is it's a probe of the sun that nature sends in very close to the sun, and we don't have to worry about maintaining radio contact or keeping it cool. We just watch what boils off.
You were talking, well, before I do my next question, let me just remind everybody here that we are talking to you from NASA Goddard in Greenbelt, Maryland. This is a live Google Plus Hangout. We are taking questions at Google Plus, at YouTube, and via Twitter with the hashtag ISON or Ask NASA. We have 20 more minutes to go. We're going till 3:30. Our two scientists here, Alex Young and Dean Pesnell, we're just talking about watching comets, and you mentioned, Dean, seeing them as brighter or darker, but I have a question here from Connie, aged 6, who would like to know what color is the comet? Can you tell her?
So the comet, when it's seen in visible light, this comet turned out to be kind of a green. It was actually kind of a pretty comet. It had a couple of different molecules that were glowing green, and it was really nice because actually we have a nice picture by a guy named Damien Peach behind us, and it was green and a little bit of blue. It had all these nice different colored stars in the picture. So that's really the only color that the comet has. When we see the comet going around the sun, we see it in wavelengths of light that you don't really see as color. We make them color so that we can see the image and kind of work with it. But we don't actually, our eyes can't see that kind of light. It's more like an X-ray or ultraviolet light than it is the kind of light that your eye uses to see. So in reality, if we looked at the comet around the sun, it doesn't really have a color to it. We did see Comet Lovejoy reflecting light, and in that case, it would have been kind of a yellowish green like anything else that's kind of white. So sorry, we don't really get a color.
And right now it's looking like we may not be able to see it after this perihelion. A lot of people out in the social media world are commenting on that and whether or not we're ever going to see it again. And people are hoping it's not. One of the questions we just got in says, is it dead, or is it just maybe just that SDO can't see it?
I would have to say that if SDO sees nothing, since we see almost every oxide, so we see anything that's a rock, that's an iron, that's any kind of carbon molecule, they all have some oxygen in them, and water has oxygen in it as well. And if it has oxygen, as it went around the sun and came out, we would have seen that oxygen. So it would have to be something that doesn't have very much oxygen in it. And I find that would be a strange kind of material to make it around without releasing oxygen like that. So, it's already surprised us once today. Maybe it will come out and we'll see it on the other side. We should know several hours from now, when the tail would start to rebuild, whether the comet will be visible again.
And let me throw in another question about survival. I'm going to throw this one to Alex Young. He is one of the solar scientists here with us today from, oh, and that means Dean is leaving, so he seems to be waving goodbye. Thank you, Dean, for joining us. He is going to go back to looking at the Solar Dynamic Observatory pictures and seeing what they're getting in on their data. Alex Young is also a solar scientist here at NASA Goddard. And the question I have for you, Dean, is from Sarah May. The question is, do many sun-grazing comets usually survive? And if they do, why? What is the difference between them and ISON?
Well, that's a really good question. The first answer is no. Most sun-grazing comets don't survive. And the main reason for that is that they're generally much smaller. As was mentioned earlier, we have this spacecraft SOHO, and up until SOHO was launched, we'd only seen a handful of sun-grazing comets from space, and even a handful from the ground. But with SOHO, we actually found out that over the past roughly 15 years, we see almost a sun-grazing comet a day. Sometimes we don't see some, sometimes we see a couple, but SOHO's seen about 3,000 or so of these things. And most of them are so small that by the time they get to the sun, they melt away and we never see them again. So in this sense, Comet ISON was actually a special comet because it's much, much bigger. But unfortunately, it seems that it just didn't have what it takes to stay together. The comet that we saw earlier, and we've seen a lot of videos for, Lovejoy, is 10 times smaller than Comet ISON, but we saw it through the solar atmosphere. So this is really a unique one, and it's unfortunate that doesn't appear that we've seen it. For whatever reason, we don't really know right now. We may never know exactly why. It just was not stable enough, or perhaps the the gravity from the sun, as was mentioned by Phil and Carl, the gravity from the sun is really, really intense, and it experiences tidal forces because the gravity is so strong that one end experiences different than the other end, and that just tears and rips and pulls at the comet. And in this case, perhaps it just experienced so much stress that it broke apart, and once it broke into these little pieces, then they all melted much quicker, and perhaps we lost it. Actually, I could add some more about that. Something that people have asked me a lot about is what happens when a comet experiences a CME. So a lot of people have asked, earlier in the week, maybe last week, it appeared that perhaps a CME had passed Comet ISON, and the question was what was going to happen. And a lot of people have been worried that a CME, when it passes Comet ISON, was going to blast the nucleus apart, and then that would be the end of it. Now, CMEs are solar material, billions of tons of solar material with magnetic field in them, but they're really, it's not very dense at all. It's spread out, and when it passed by the comet, it actually didn't have enough oomph to blast the comet apart, but what we do know is that sometimes the magnetic field of the comet can pull at the comet's tail and rip it away. And we saw this several years ago, back in 2007, I believe, the comet Encke, and we saw it swimming along like a tadpole in the stereo imagery, and sure enough, a CME swept past it, and the tail just disconnected and then moved on away, and then the tail reformed. So we know that CMEs will interact with comets, but as far as we can tell, there's actually no real structural damage that can be caused by a coronal mass ejection.
So, Alex, you just preempted me. I was actually going to ask you that question from one of the people who sent in a question. Let me just describe for everybody, a coronal mass ejection is this huge eruption of solar material that comes off of the sun. It's a big cloud that explodes out into space, and it's just gigantic. And so this is the kind of thing that that Alex is talking about, passing by the sun. It's called a coronal mass ejection, or a CME. And the question, just so he gets acknowledged, was from Kevin Dingo. The question was, is there a chance that a CME could have knocked Comet ISON? So I will ask you a different question, Alex. We'll move on to a question from Prince K. Max, who wants to know, is it a myth that comets are a ball of fire? And is it true that the gases within the comet are flammable, causing the sun to set it alight?
Well, that really is is a myth, in that a comet is not a ball of fire. I mean, you have to have oxidizers to have fire, and in space that's not the case. So it is really basically just a ball of ice that once it gets close to the sun, then the ice is melted away. So no, it's not a fireball, and it doesn't really burn up when it gets to the sun. It just melts. Even the rock and dirt melts. Actually, I wanted to go back and show, in relation to the previous question, I think I can show a video of what happens when a comet passes, a CME passes a comet. So I'm going to switch over real quick, and let's see if this shows up.
And while you do that, Alex, I will just remind our viewers that we've got 10 more minutes here at this live NASA Google Plus Hangout. We've been having a great time in the Solar Dynamics Observatory Mission Control Room. We have not been able to see Comet ISON in its last slingshot around the sun. We were hoping to see it with this solar observatory, which is up in space, but it has been seen over the course of the last week. Scientists will be studying this comet for many of the next years, as we've been able to watch it for the last year coming in towards the sun. It's been an exciting ride. If it has indeed broken up today, which few of the people on here today have suggested, well, it's still going to make some great science. And with that, I'll pass it back to Alex, who seems to have found his movie of a CME. Yes?
Well, I've got what I've got now is an animation that I want to show folks. See if I can get this to work. And by the way, I did just get a message from one of the scientists for SDO, and so far they say that they do not see ISON. So it's not looking too good. So let me see if I can get this to play. Okay, so can you guys see this animation? Okay, so what I'm showing, I think this is actually more easier to illustrate. You got this comet traveling along, and then a big coronal mass ejection that's solar material and solar magnetic field sweeps the tail away and disconnects it. So this is what we think happens when a CME passes by a comet. But really this interaction is an electromagnetic interaction, so it doesn't have a real strong physical impact to the comet's nucleus, so it doesn't really break it up, but it does sweep the tail away. And this is something we've seen a couple of times now, and I'll go really quickly to some real data and see if we can look at this real quick. 1 second. So, okay, so now we're looking at real data. So this is data from 2007 from the STEREO spacecraft, and there's a coronal mass ejection, and you see that Comet Inky is flying past it, and when the coronal mass ejection hits it, it takes the tail away. It's a little bit difficult to see, but it's pretty cool. So that's what I just wanted to show everybody.
Great, thank you, Alex. We are wrapping up here. We've had so many questions from our viewers, and we're sorry we didn't get to all of them. We really appreciate everybody watching us today. We're going to answer just a few more questions and maybe take a last look at some of the data that we've been getting in. A reminder that I'm Karen Fox here in the Heliophysics Division of NASA Goddard Space Flight Center. We've been talking to a great bunch of scientists today. Our last one is still with us. That's Alex Young, a solar physicist here at Goddard, who has been with us. And the last question, maybe not the last question, but one of them. Oh.
Can I add something really quick? So I just wanted to say one thing. So we've gotten so many great questions, both at the NASA sites, and I've gotten a bunch on my site, The Sun Today, the Facebook page. And so I'm going to try to gather up a lot of these questions and answer some of them offline. I'll post them up on thesuntoday.org and the Sun Today's Facebook page, and any of the ones that would come from NASA. So it'll take me a little while, but I'll try to make sure that as many of these questions gets answered, because we've had so many great ones, and I don't want people to be left out. So I just wanted to throw that in.
Great. We'll be just finishing up with the last few questions. I have one from Charlestown Weather, and they would like to know if we can expect any meteor showers. Even though the comet is broken up, will some of the debris create some shooting stars for us?
Well, I think that since it's not making it past the sun, I don't think we're going to get much in the way of debris at this point. So I don't think we're going to have any great shows from Comet ISON, unfortunately. But we were looking forward to that.
Just a reminder that I think, and you correct me if I'm wrong, Alex, but to get the meteor shower, we really had to get those pieces a lot closer to Earth, and the closest approach to Earth was expected to be December 26th, and it's still pretty far away from us for that to actually interact with Earth's atmosphere. And the question everybody wants to know, and it's being asked in this case by, I don't know if I'm going to pronounce this correctly, Ilgaz Owner Tas, wants to know what happens next. Are we going to be able to see another comet near the sun in our lifetime?
Well, the answer is yes. We're going to see more. Hopefully they're going to be big ones. That's what we want. We want big ones. So we see them all the time with SOHO and STEREO, And they're quite amazing. So you can go to the NASA sites, like, for example, stereo.gssc.nasa.gov or soho.www.nascom.nasa.gov. Those are great sites. You can Google SOHO and STEREO NASA. So you can see comets all the time. But also, you want to go to, Carl has a great page at NRL that's Sungrazer. Just do a Google search for Sungrazer and NASA, actually. And Carl's site is fantastic. He keeps up with all of this. So anyway, yes, we're going to see more Sungrazers. What we have to hope for is that we see more big Sungrazers, because most of them get melted by the time they reach the sun. So we want to keep our fingers crossed that we get a couple more of these kilometer size, or even Lovejoy was only 100 meters in size. And if we get some more of those, and they have this a good possibility that we get to see another show.
So we are wrapping it up here, and the Solar Dynamics Observatory Mission Control Center. We've had a great time here today with the scientists who have been able to join us. Alex Young is the last person standing before he leaves for his Thanksgiving meal. Alex, can you wrap up for us? Tell us what was exciting about this whole journey for ISON coming in, what, if anything, was disappointing or exciting about today, and there's some chance we'll be able to pull up, while he's talking, the last imagery from the Solar Dynamics Observatory, the live imagery we've been watching. We're trying to get that up for you as well. Thanks.
Well, this has really been exciting because of the anticipation. One of the things that's been so great is that we've known about this comet for over a year now. We've been waiting for it, and the solar physicists have been really looking forward to it getting to the sun. When we saw Comet Lovejoy, it was unbelievable. We were so excited. We saw it go behind the sun. We didn't actually know if it was going to make it or not. And I remember vividly sitting at my computer. I know my colleagues were down the hall, and we were waiting and waiting. And as soon as we saw the first image, it was incredibly exciting. So, to tell you the truth, that's what we were looking for here. We were really hoping that we were going to see this, get some spectacular imagery in SDO, and that's disappointing. Yes, it is disappointing, but that's what's the excitement, the anticipation. So we're really looking forward to that again. We've learned some amazing things from past comets that have come past the sun and seen with SDO, and I hope that we're going to see this again. And I really appreciate all of the great questions and the great support. This is really, really exciting. We all do this because we love it, and do a lot of this even on our own time, just to try to share with you all the amazing data, the amazing science that we get to see. And we really appreciate all the support, and we'll try to continue to answer your questions. Also know that all of this data is going to be online. A lot of it is, well, no, I'm saying not just SDO data, but SOHO data, STEREO data, all of that. Some of that comes in as quick look data that will be processed in better quality. So all of it will be online in addition to the SDO data, which is online right now. You can go to the SDO website and go straight to the ISON data page, and you can download videos. You can see it in real time. So thanks, everyone. It's really been a pleasure, and have a good holiday.
And I'm going to peel back the curtain just before we say goodbye. Thank you to everyone for joining us, but I want everybody to see all the people who have helped us today. We have a room full of people who have given up just a few hours of their Thanksgiving. Everybody's been here. And
Happy Thanksgiving!
Happy Thanksgiving, everybody! We're all going off to eat our meals now. Enjoy yours. Thank you. Bye from NASA.